Hello everyone, this is Professor Sharvari Patil and in this video we are going to study about sampling, quantization and aliasing. So before moving to the sums on sampling, we will see the block diagram of digital signal processing of analog signals. All the signals present around in the environment are analog signals. So to give it as an input to a digital signal processor, we need to convert this signal, analog signal, to a digital signal using analog to digital converter. After getting digital signal as output, this signal there will be processing operation performed on this digital signal and you will get output as a processed digital signal, which is at the end given to digital to analog converter, which will give you an output as an analog signal which is given to the users. So basically, you looking at this diagram, it is clear that we need a digital signal to perform certain operations on it. So how do we get a digital signal? To obtain a digital signal from analog signal, two steps are performed. The first step is sampling and the second step is quantization. So what is exactly sampling? In sampling, we collect discrete samples from the continuous waveform of an analog signal at a regular interval of time Ts. And quantization can be given as an example of rounding the values that we have got in sampling to the nearest millivolt. These diagrams give a clear idea of what is sampling. In this first block, you can see a continuous waveform which represents an analog signal xt, and we have collected samples at a particular interval from this continuous waveform. In this last block, it is very clear that we collect samples at a particular interval, and this entire collection of samples from a continuous waveform is called as sampling, and the output of sampling procedure is a discrete time signal, or it is also mentioned as a dt signal denoted as x of n. Now sampling will lead to potential loss of information because we do not collect all the information that is present in the analog signal, but we collect the samples at a specific interval of time. But our sampling rate must also exceed to the highest signal frequency FO. Now what is Nyquist sampling rate? Nyquist sampling rate is 2 times Fmax as mentioned here. Nyquist sampling rate is 2 times Fmax, and if our sampling frequency is less than this Nyquist rate, there is a phenomena that is called as aliasing which takes place. Now what is aliasing? Aliasing is nothing but a false effect that occurs in your signal. So the simple example of aliasing can be a wagon wheel effect. Those who are not aware of wagon wheel effect, after a particular speed of a wheel, it appears to be moving in a reverse direction, which is actually a false information. So that is called as wagon wheel effect, and it is an example of aliasing, which means that a wrong signal or a false information is conveyed to the end user. So when does this occur? What is aliasing and when does it occur? Aliasing occurs when our sampling frequency is lower than the Nyquist rate. And what is Nyquist rate? Nyquist rate is 2 times the Fmax, that is maximum frequency. So now we will see how to solve sums on sampling. So basically what is sampling? We convert our any signal xt to xn, where xn represents a discrete time signal. So to perform this operation, what is done is we just substitute t is equal to nts, where ts is the time at which we have performed the sampling, which can be denoted as n is equal to 1 by fs. So what is fs? Fs is nothing but the sampling frequency which is given in hertz. Okay, so always remember this, that sampling frequency is given in hertz. So let us take the first example where xt is given as phi sine of 20 pi t plus 10 cos of 200 pi t. Now this is the equation that is given, and sampling frequency is given as at 80 Hz, and we have to find the sampled discrete time signal. So let's see the solution. So like I have told you, to convert any signal xt to discrete time signal, what we have to do is we have to substitute t is equal to n ts, where ts can be written as 1 upon fs, where fs stands for the sampling frequency. So let us substitute the value of the sampling frequency fs. So n divided by 80. So wherever you have t in the given equation, we have to substitute it as n by 80. So let's start. Okay, so xn instead of xt, now we have written it as xn. So xn is equal to phi sine of 20 pi, and instead of t I am going to write it as n upon 80 plus 10 cos of 200 pi. Again instead of t I will write n divided by 80. Now I have to solve this sum, that is I just have to find the values of 20 by 80 and 200 by 80. So let's do that. So phi sine of 20 by 80 is 0.25 pi n plus 10 cos of 2.5 pi n. Okay, so this is my equation xn, which I have got from discrete continuous time signal. Now this 0.25 and 2.5 are written as omega 1 and omega 2. So what is omega 1 and omega 2? Omega 1 and omega 2 is nothing but digital frequencies, and omega values, that is the digital frequency, has a specific range, that is omega lies between minus pi to pi. So looking at the values of omega, you can see that the values of omega 1 is within the range of minus pi to pi, but omega 2 has exceeded the range of minus pi to pi. That means it is 2.5 pi. So whenever such condition occurs, when your omega value gets exceeded from minus pi to pi, we have to subtract it by a value called as 2 pi. So now when I solve this sum further, my omega 2 value will be equal to 2.5 pi minus 2 pi. So the new value of omega 2 is 0.5 pi. Now what I will do is I will rewrite my discrete time signal xn, which I have got, using the new omega value. So now my xn value is equal to phi sine of 0.25 pi n plus 10 cos of 0.5 pi n. So this is clear that simple any kind of equation that you get, what you have to do to find the sampled signal or a discrete time signal is you just have to substitute the value t is equal to nts, and fs will be given in the question. If fs is not given in the question, what is to be done we will see next. 0.04 pi n plus 10 cos of 200 divided by 500 is 0.4 pi n. Now if you observe this equation xn, you will see that the omega values, that is omega 1, right, and omega 2 are within the limits of minus pi to pi, right, from minus pi to pi. They do not exceed this limit of minus pi to pi. Correct. So we will leave this equation as it is, and this is my signal x of n, which is a discrete time signal. Now in the question, if they ask that I have to reconstruct the given signal, okay, so I have to see whether the reconstruction is possible or not. So the step for reconstruction, what we have seen till now, to convert a continuous time signal to your discrete time signal xn, what is the substitution that we do is T is equal to N upon Fs, right? So this will give me sampling, right? So now if I want to reconstruct from my discrete time signal, that is from xn to xt, means I need a substitution which is equal, says that N is equal to T into Fs. So very simple for reconstruction. So let's see how to perform reconstruction. So for reconstruction, like we have seen, what is the substitution? N will be equal to T into Fs. So what is the Fs that we have considered here? We have considered Fs as 500. So we have to substitute N is equal to 500 T to get back our continuous time signal. So simple, we just have to substitute now. Xn is equal to phi sine of 0.04 pi, and instead of n I have to write it as 500 t plus 10 cos of 0.4 pi into 500 t. Okay, so now when I perform this multiplication, I will get the signal back xt, which will say as 5 sine of 20 pi t plus 10 cos of 200 pi t, right, which is our question. So we can reconstruct back our continuous time signal, and what is the reason for this reconstruction being possible is that we have taken our sampling frequency Fs, which is greater than the Nyquist rate. This is the reason because of which we could reconstruct our signal back, and we could get the original signal back when we perform this reconstruction operation. Similarly, if you can take the first example that we have solved. Here in this first example, our sampling frequency was 80 Hz, right? Can you see here in this first example, our sampling frequency was 80 Hz, and which is less than the Nyquist rate. For the same sum, the Nyquist rate is 200. We have seen the same question. So this here in this example, we have not taken the sampling frequency greater than the Nyquist rate, and hence if we try to perform reconstruction on this xn, we will fail to get back our original signal. Okay, that means if we try to substitute here now, from if this is my xn and from this xn I want to get back my xt, this is not possible because now what is the substitution that we perform? We perform t is equal to n by 80. So to get back the signal, I have to write it as n is equal to 80t. But if I substitute here 80t, I won't get back my original signal. We will see it by solving. So x of t will now be equal to 5 sine of, if I am trying to reconstruct it, 0.25 pi into 80t plus 10 cos of 0.5 pi into 80t. So this is not going to give me back. This will definitely give me 5 sine of 20 pi t, but it will not return 10 cos of, what it is going to return here is, it is going to return it as 40 pi t. So this is not same as the question that we are trying to solve. So this xt is not the same. We have, instead of 40, we have 200 here, right, in the question. So we could not reconstruct the signal since this sampling frequency that was considered as 80 was not greater than the Nyquist rate. So I hope you all are clear about what is sampling frequency, how do we reconstruct, what is the aliasing effect. So the takeaway, I'll just give you a short feedback, or I can give you a short recap of what we have done right now, is that we have seen how to sample a continuous time signal into discrete time signal xn, and we can perform this sampling by a simple substitution as t is equal to nts, and which can be written as n upon fs, fs being the sampling frequency in hertz. This is sampling. And if I want to reconstruct my signal back, that is from xn, if I want to get back my continuous time signal, then my substitution is n is equal to t into fs, right? So reconstruction is possible only if sampling frequency is greater than or equal to Nyquist rate. And how do we find Nyquist rate? Nyquist rate is equal to 2 times f max. We have seen how do we calculate the maximum frequency, and these are the few points you have to remember about sampling, reconstruction, aliasing and Nyquist rate. So when I say reconstruction is possible, means there is no aliasing. I hope all the points are clear from this section of sampling, quantization, reconstruction and aliasing. If you like this video, do share and subscribe. Thank you.